With a presentation of Udo Seifert from Stuttgart University. He will talk about classical contributions to the field of stochastic thermodynamics. And Udo, please.
Thank you. Can you hear me? Does it work? Yeah. Good, perfect. Yeah, first of all, I'd like to thank Edgar as the local organizer, and of course all his colleagues from the OC for the invitation and for putting this together. I think it's wonderful that after this pandemic we can meet in person and exchange ideas. It's the last day, and some of the topics I will raise have been touched by others, but since it's a somewhat wide audience, I thought I should still keep an introduction. And the basic idea, of course, what I'm doing is based on developing and refining stochastic thermodynamics, and the basic idea of stochastic thermodynamics is shown here. So you all know 200 years ago people wanted to understand and optimize these kind of machines, and more recently, due to experimental progress, it has been able to look at molecular rotary machines on a much smaller scale. This is the F1 ATPAs. And when you attach a big particle to this F1 ATPAs, you can actually see distinct 120-degree steps. And you have to appreciate that each step here is associated with hydrolyzing, let's say, one ATP. So we see here discrete chemical events. And then the question is, can the concepts of thermodynamics which have been developed 200 years ago, can they be applied to these kind of machines? And it's obvious that fluctuations will play a significant role. So how do we integrate these kind of fluctuations into a thermodynamic understanding, an understanding which, for instance, would lead to the notion of efficiency of such a machine as well. And then it's obvious that these fluctuations play a significant role. So the idea is that I briefly introduce stochastic thermodynamics. I will be using simple biomolecules as a kind of paradigmatic system. Then I'll talk about the uncertainty relation and what you can do with it. And in the second part of the talk, I want to come to recent work on waiting time distributions, and then close with talking about the minimal universal cost of having an oscillating biochemical system. Okay, so let me start with, I think, a really beautiful pedagogical experiment. I mean, you can use it when you teach. They didn't certainly not think of it as a pedagogical experiment, but what they did, this was Matthias Reeves' group some 10 years ago. They took a small peptide, connected it to these beads, which you can manipulate by tweezers, and then by applying forces, you can create a situation where when you measure the length, even at constant force, it jumps between discrete values. And through a careful analysis of this length at given forces as a function of time, so these are single molecule trace, they were able to discriminate between 6 different conformations or mesostates. And the nice aspect of this experiment is that they analyzed transition rates between these states, and they could show that this is a Markovian dynamics. And for me, this is one of the nicest examples where you can introduce the idea that you observe such a system in the course of time. You have different states, and this is one condition for being able to have a thermodynamic interpretation. So again, here the boxes are the mesostates. Of course, many microconformations contribute, but if you have this timescale separation, then on the level of the mesostates, capital I here, you get this master equation with transition rates. Now you can measure these transition rates, and the ratio, how do you measure them? You just look at a long trace and you record the time the system spends in J versus I, and from this ratio, you get a free energy difference between these mesostates. Sorry, this should be capital indices here. And if they had done the experiment at different temperatures, you could even split this free energy into internal energy and entropy. This is something they haven't done yet, but I think somebody should do these kind of experiments. So now we have thermodynamic potentials for each of these 6 mesostates. For full-fledged thermodynamics of biosystems, we need one more ingredient, which is we have to allow for enzymatic reactions, for chemical reactions. As you know, much of this is going on when you look at a process like protein synthesis, for instance. So some time ago, we thought about, how would you identify a first law on the level of single events? So suppose you have an enzyme here, different conformations. Let's say A1 is ATP, A2 and A3 are ADP and phosphate. Well, it's not too hard to figure out that for instance, the chemical work you put in is the imbalance in the chemical potentials of these ATP and so on. There's an internal energy in the way I just described, and then when you're careful, you can identify heat correctly. And just as a side remark, heat is not necessarily entropy production. Okay. So I will mostly talking about non-equilibrium steady states. And one of the paradigms, this is not bio, but I needed to make a point, colloidal particles are driven across, for instance, periodic potentials. So you drive this particle with a non-conservative force. You identify entropy production with this log ratio, which Juan yesterday talked about. And then there was a major insight of finding, first numerically and then theoretically understood, that in such a steady state, if you measure entropy production or identify it along a single trajectory, this distribution then obeys this kind of symmetry, which is called the fluctuation theorem. And that's one of the pillars of the field. So let me show you how this distribution looks like for this kind of situation. We did this experiment 15 years ago with Clemens Bechinger. So here you see the red histogram is the entropy production after 2 seconds. The black one here is after 20 seconds. So these are non-Gaussian, strange distributions. However, when you plot them in the way that you compare the probability of getting negative entropy production, you find in the logarithmic representation a straight line. And of course, experimentally, you always have errors, you have problems with statistics, so you can't do that for too long a time, because then, as Juan said, the probability of getting negative values is too small. So if you look at this slope as a function of time, it should be 1, and it is almost 1 in this experiment. So what have we learned through this experiment? Nothing. We learned that this system obeys the Langevin equation, because once you have this, this is a theorem. And this is the problem of this beautiful relation. It's essentially useless, except for one statement, a binary statement you can make, and I want to illustrate this coming back to this molecule. This group, 10 years ago, tried to apply the fluctuation theorem to measurement of traces I've shown you on the first slide. So they measured the angle distribution after a certain time. And when you take the angle as a proxy for entropy production, then you would plot, or you would try to apply this fluctuation theorem, and indeed they get a nice straight line. However, the problem is that this slope from which you would get the torque, that this slope depends on time. So this shows that there is a problem, and that you can't take this angle as a proxy for entropy production. And the reason is quite simple. There are hidden degrees of freedom here. So what you see is the observation, you observe the motion of the bead. However, there is also this motor, and then there's some elastic linkage between the motor and the bead, and you can't see directly the motion of the bead. You only see, of the motor, you only see the motion of the bead. So when you transform this insight into a simple, really simple model, just here a linear one for simplicity rather than rotary, you have the motor which does these 120 degree steps upon a hydrolysis of ATP, and it drags along this bead which you measure, and then there's some elastic linker. With this model, you can actually reproduce these data very, very well. But it's a model. Once you have the model, you can even use it, for instance, to look at efficiency. And we have seen this Harada-Sasa relation before. Toyabe and co-workers use this. difference in a sense between a response function and correlation function in order to get information about dissipation. These were their data. We take our model, and again, within the error bars, we reproduce this data. But, and I want to emphasize this is a model. And the real tool or the real goal should be to get tools that enable inference without putting in too much of a model. And that will now be my main part. And before I start with this, I have one slide for Christian. There are two aspects of the relations I will be showing to you. Even if you don't like entropy production, or if you don't think entropy production is worth measuring, you might want, for instance, to have a precise watch. So the kind of inequalities I will show you can be interpreted in two ways. You'll see you have inequality, sigma entropy production is larger than something which you can measure. Yes, then you get a lower bound on entropy production, but you may not care. However, if sigma is larger than something which is desirable, this relation will tell you the minimal cost of achieving something that is desirable. So this is a dual aspect of these relations, and I want to start with the second aspect. Suppose you want to build a watch, a clock, which works at finite temperature. Question is, and that's actually how I got into thinking about or thinking along lines which led to the uncertainty relation. I wondered whether a more precise clock would draw more energy, would need more energy from the battery. And the answer is, for a huge class of clocks, we now know that in order to have this clock operating at a precision of 1 second per day, you have to spend at least 10 to the minus 11 joule per day. How do we get to this number? Well, you'll see in a minute. Okay, so what do you do as a theorist? Well, you build a simple clock. And the simplest clock is one where when the hand advances, let's say, one second, for instance, you get the energy from ATP because we want to apply it to a biocontext. So each forward step with the rate k plus will happen, for each such a clock, you will have also a probability for stepping backwards. And for instance, if you want that after 1 minute you have made 60 steps, this will happen on average. But sometimes after 1 minute you will have 58 or 62 because this is at finite temperature. There is a variance or a diffusion or dispersion to it. And of course you all know how to calculate this. And with these quantities we can define or identify an uncertainty, which is this variance divided by this output squared, or the mean. Now, as I said, there is a cost to this, and using the rules I tried to briefly sketch at the very beginning, it's easy to calculate the entropy production, i.e. the free energy cost. This is given by this log ratio, and here the current. And the ratio of these rates is related to the driving affinity, the imbalance in chemical potentials. And when you put all these trivial relations together, you find that the product between cost and uncertainty is given by this hyperbolic function, which is larger than 2 kBt. Now, the real surprise is that this will work not only for the asymmetric random walk, but even for a Swiss watch, where you have error corrections, epicycles, whatever. So you build an arbitrary network of states with transitions between those. You have one coordinate in the sense where the clock advances, and then the uncertainty relation tells you that this box holds. So for instance, a temporal precision of 1% will cost you 20,000 kBt, irrespectively of you can't beat that. Okay. By the way, I would like to have questions during the talk. Please interrupt. Now let's use this and put it into somewhat, I think, useful for this audience context. So I will show you that you get now statements about the efficiency of molecular motors. And again, I want to start with old data. This was from Steve Block's group, 99, one of the pioneering experiments, kinesin walking along a microtubule against a feedback-controlled constant force. What they measured at the time was the velocity, the diffusion constant, i.e. dispersion in the velocity, which they quoted as this ratio called the randomness parameter. And data look like this, right? This is the randomness as a function of ATP concentration for various applied loads, or as a function of the load for constant ATP concentration. Very nice experiments. You get this kind of data. What do you do with it? You come up with a model for the motor, try to fit it. That was, in a sense, phase one. What we now can do with the same data is the following. Entropy production in this situation is the difference between what you put in and what you get out. What you put in, you do not know, because you do not see when an ATP vanishes without assuming that you need one ATP for one step. So what input is inaccessible, the output is clear, that's just velocity against this externally imposed force. We do have, however, now this inequality relating entropy production with the mean current, i.e. the precision, and the dispersion. Now, what is efficiency? Efficiency for any mechanical engine, or any engine putting out mechanical power, is power output divided by input. And this input we can relate to the output and what is lost. And now we are in business because for the sigma we have this inequality which you transform into this right-hand side. And the nice aspect about the right-hand side is that everything is an experimentally controlled or measurable quantity. You measure the force, you measure the dispersion, you measure the velocity. So these are the data from the previous slide, and overlaid is in color is this function here. So let's take this point here. I'd like to explain it with this point. This point is at 2 piconewton external load. Randomness, i.e. ratio between velocity and dispersion, was about 0.4. Our curve here tells us that this is the 45% line. So the statement which we can now draw is from this comparison is the following one. Under these conditions, does this motor does transform at most 45% of the chemical energy into mechanical work. This is the hard statement, and this is a model-free statement. I'm not saying it's exactly 45%. I'm saying it's definitely not more than 45. It could be much less, could be 3%, but it's certainly not more than 45, and I think that's the first time you can make a statement like this, model-free. Just as an example, what stochastic thermodynamics now with this more refined tools, inequalities can do for you. And I would encourage all experimentalists to take their data and to try to apply this relation to it. Okay. Yes, please. Joe.
You know, I can't read the labeling on the right-hand graph, but that's the 45%. What are the other ones?
Oh, yeah, sorry. This is 70. This is 85. This is 15.
Okay. Yeah.
No more than, so at this very weak load, it's no more than 15%. No more than this. So this is, the upper right corner is forbidden.
80% is a weak. 80% is a weak.
A weak bound.
Yeah.
Maybe
100%
a
is
weak
very
bound.
weak
Yeah,
bound.
yeah. Maybe a rather weak bound. Sure, certainly.
Yeah, so there was this presentation by Felix where he had the bound on the other side.
Yes.
So does this mean that now one can establish a lower and an upper bound for efficiency?
You have to ask Felix. I haven't transformed his bound into this kind of idea. Sure.
Sorry.
I'll repeat it, Felix.
Works. Oh yeah, it's always the same question I ask you in the seminars. At equal, so what I have difficulty to understand is at zero force. So a motor that translocates at zero force, right, without load, without applying a force, if you put F equals 0, you get the efficiency 0. So, because...
Yeah, yeah.
So I never understood this thing. And
Well,
I don't know
this is because you define efficiency as the mechanical output. You can define Stokes efficiency, and then it's a different story. And I don't have this for Stokes efficiency.
So how can we experimentally test?
Well, you repeat Bloch's experiment. You apply a constant force. That's what tweezers are for.
Okay.
Yeah, Anatol.
But we do know, I think the experiments were done by Joe, by others. They know that in this system, they definitely spent 1 ATP. They know this, right? They proved it by using different biochemicals. Yeah. So there is another estimate of the same quantity, how it compares with your number. You understand, right? You know the work, and you know that only 1 ATP is consumed. You know biochemical conditions. You know this energy.
If you know that for each step you use exactly 1 ATP, yes, then it's a trivial calculation to calculate the efficiency. It's force times distance divided by this 1 delta mu.
My question, how it compares with the numbers that you are producing?
I haven't done that. Okay. Somebody should do it. Perhaps, yeah. Thank you. If you have more information, you might be able to tighten this. I haven't done that yet. Okay, so this was steady state. Now let's go to time-dependent generalization of this uncertainty relation. This is a theory slide, but I'll show you an application to an experimental situation on the next one. So time-dependent driving means that these rates now depend on a control parameter lambda, which the experimentalist can change by turning a knob. And we assume that turning this knob can be done at various speeds. We observe the system at total time t. And now you can, for instance, look at what is the total time or fraction of time the system spends in a state I. And the generalization of the previous statement is that if you look how this mean time changes with the observation time and how it changes with the speed with which you change your control parameter, and you measure the dispersion, again, in a time-dependent situation, you have this lower bound on the entropy production, which now, of course, depends also on the speed parameter. And you can use other observables. You can just take the observable, what is the final state? So this is a kind of characteristic function of state I. And suppose you now measure how these observables, how they change when you change the control parameter, you plug that in, you get an estimate on entropy production. We did this in exactly the Reef experiment situation. Since they have measured all these rates, we have no, in a sense, we have no free parameter. So we now assume a time-dependent situation where we ramp the force. We unfold under force. And for instance, we can just look, is the system at the final time in state 1, 2? This is one of these partially folded ones. Or what is the total time spent in the unfolded state? And since we know all rates, we can calculate the entropy production exactly, and we can use the estimate from the bound. We look at the ratio. This ratio is shown here as a function of the speed. And what you should get away with here is, or take away, is that you get something between 20 and 80% of the total entropy production, depending a little bit on condition. So again, this is a model-free estimate. So you just do the experiment. You don't even need to know the force. You just need to know your knob with which you change things. And again, this is something which hasn't been done yet in real experiments, but whoever has a nice time-dependent situation, I would like to encourage him or her to use this for getting the entropy production. Okay. Now, yes, Joe.
How does this relate with, the Dudko theory where you go from, is it related to that? Because
no, not at all. Dudko is a model. You put in some potential. You look how the barrier changes with the force.
But given these force ramps, you could calculate force-dependent, transition rates.
I could do, but I would have to put in an underlying free energy landscape for this kind of Gramercy scape. This is what I call model-dependent. This would be model-free. Of course, it's interesting to compare it in specific situations. And in a sense, with their data, we have done a specific comparison. And that's why I get these numbers, because I can calculate entropy production exactly if I know already.
Sorry, Udo, can I ask you?
Sure.
Maybe it's a naive question. So when you do AFM experiments,
Yeah.
right? And if you try to break the bond, if you slowly do it, you break with one force, but then you try to do ramp up, and it's a different force. So is there any implicit assumption that you're still at equilibrium all the time, or
no.
not?
There is the implicit assumption that you still have these mesostates.
Mesostate, that's
So
fine. But the question what I have problem is the force of bond breaking will be dependent on this parameter.
That's okay. I mean, you can even have different paths in your landscape, and that still applies.
Interesting, thank you.
It's general. Okay. If there are no further questions, I'll come to the second part, which is about this using waiting time between transitions. So for the tour, you just count how many transition in this direction, how many in that direction, mean and dispersion. Now you take the time between transitions seriously. So suppose you have a simple, I should say, I mean, many groups have started this. We had major proponents already talking about this. I will be talking about what has been published here. I should say that Edgar and co-workers did essentially the same thing independently, and we submitted within 1 week. An incredible coincidence. So suppose you have a four-state network, and suppose you can only see the transitions between 2 and 3. But now you take the times where these transitions happen seriously, and in particular, you take the waiting time between having 2 consecutive transitions, 2 to 3, or 3 to 2, 3 to 2 here. So these waiting times look like this, and the crucial quantity for the following is the log ratio of the waiting time for 2 plus transitions compared to 2 minus transitions. Now, once you have worked on it, it's easy to show that in a unicyclic system, so suppose this transition between 1 and 3 wouldn't be there, so you only have 4 states, 1 cycle, you only see transitions between here. This log ratio is time independent and gives you directly the affinity, the driving affinity of this unicycle. Since the current can be inferred from these measurements as well, you get the full entropy production by just looking at 1 transition in this unicycle. And when I saw this first, I was kind of surprised and impressed, because it's better than the tour. From the tour, even in the unicycle, you do not get the full entropy production. So this already shows you that it's potentially very strong. Of course, the interesting systems are not unicyclic, so if you have a multicyclic system, and let's again assume you only see this transition between 1 and 7, this log ratio of forward-forward divided by backward-backward as a function of time, it becomes a function of time. And such a curve includes or reveals interesting information. Suppose, there is a minimum and there is a maximum, and what you can prove is that minimum and maximum of this log ratio give bounds on the maximal and minimal affinity of all cycles to which this link contributes. So now you get more than entropy production. You get more, more local information, and you get even topological information. You also can extract the minimum number of states included in this cycle. And again, we did 2 million networks, looked at the quality factor, which for us is always the ratio between bound and truth, and typically you see it's between 20 and 80%. Okay. Of course, if you have more information, for instance, if you observe now these transitions and these transitions, you have a whole matrix of these waiting times, and then you get better bound. So essentially, you have this kind of, well, almost Kullback-Leibler looking quantity as a lower bound on entropy production. And you even get a criterion whether for having here equality. If all of these ratios are time independent, you can be sure that you see everything. You get the full entropy production. Okay. This was still looking at transitions. I now want to show you that from time symmetric information, you can infer entropy production as well. So this is a somewhat busy slide, so let's first look at this corner here. Suppose you have this network and you only observe whether you're in state 1 or whether a transition happens here, but you cannot resolve the direction of this transition. So the effective network, in a sense, looks like this. You are either in 1 and occasionally you see a transition, but you do not see the direction. But when you now measure the waiting times between, let's say you observe 3 G transitions, you have 3 times here, and again, you take the reverse direction, put it in the logarithm, you get a lower bound, a non-zero bound on this sigma whenever there is a cycle current here, even though you do not see a single event which under time reversal would look different. Okay, and you can, for instance, in such a network, if you look at waiting time, suppose you only see 1 and these transitions, from these kind of statistics, you can infer whether or not there is a hidden cycle here, even though you do not see a single state. Okay. Let me now show you recent work we did where we tried to apply this to this molecular motor situation. And I think this relates also a little bit to what John had in his talk yesterday. So let's take this situation and suppose you know the force you apply to the bead and you observe the motion of the bead. You do not know the entropy, you do not know the delta mu, since you haven't measured, for instance, the chemical potentials. And let's assume you even do not know the discrete step size of the motor which is pulling this bead against the force. So what you now have to do is the following. You have to guess a step size, which I call delta x, and you have to record the times when you reach this delta x. And you can reach a delta x upwards or downwards. The upwards is a plus transition, the downwards is a minus transition. So again, you record this statistics between subsequent pluses and subsequent minus. And what can you do with that? There are 2 regimes. Let me first explain what you might call the trivial one. So suppose you have strong coupling between the bead and the motor. Then the traces look like, let's see, yeah, traces look like this. So you see, in a sense, you see already the steps. What you do is you look at this ratio as a function of your assumed step size. Let's call delta x an assumed step size. And if you look at the time dependence, you will see if you have chosen the correct step size, this is constant. This is a constant value. You can also look at the log ratio of for the probability of having 2 plus transitions compared to 2 minus transitions. And then you plot this as a function of the delta x compared to the true step size. It should become constant when you choose the correct step size. And then you actually get the delta mu from such data. Now you might say, I'm not too impressed because I see already the steps. But now suppose you have a weak coupling between motor and bead, then you do not see the correct steps. You hardly see any defined steps here. You do the same analysis and it still works. So again, I think it would be interesting to apply these ideas to real motor data. Okay, now in the last 5 minutes, I want to talk about the cost or the inference from observing or wanting to create biochemical oscillations. And of course, one of the famous ones are these circadian rhythms, which people could reconstitute in a sense in a test tube. So you have this chi molecules, you put in some ATP, you look at the expression level of one of those, and you find nice 24-hour cycles. So the point, of course, is not just to create these oscillations, but you want these oscillations to be phase stable. You want these oscillations to be coherent. Again, you could expect perfect coherence will cost you an infinite amount of free energy. But what is the precise relation? That's the question. Okay, again, this is work with Andre, started some time ago. You build the simplest one, and that would be a unicycle. I've drawn here just 3, but the data here are, suppose you have 100 states, you drive it with an affinity of 200, you get this kind of decay of the oscillation. So what is plotted here is the probability of being in state 1 at time t when you have been in state 1 at time 0. And that's the coherence, or the decay of this is the coherence. And this calligraphic N tells you that after 4 oscillations, basically you have lost the phase stability. Now, for such a simple unicycle, as a function of number of states n and driving affinity A, you can calculate this ratio exactly. You can also calculate the free energy cost per oscillation exactly, and what you find are these kind of bounds. Now, we did a lot of numerics for multicyclic networks. And based on this numerics, in 2017, we conjectured that this bound which you get from the unicycle extends to a multicyclic network in the sense that you have to take the best cycle. And this was out for 5 years, and I was very pleased to see just this spring a mathematical proof of it. And if you look at this paper, it's really hard. I don't think we should feel bad that we were not able to show it mathematically. The more interesting bound from a physical perspective, in my opinion, is this one, which we also more recently conjectured. That is the cost per oscillation as the function of the coherence. So the statement is each oscillation costs you at least 4 pi squared times the number of coherent oscillations you have in your system. So the more coherence you have, the more you have to pay for a single oscillation. And this is independent of the drive. You don't need, the driving force doesn't enter, the number of states doesn't enter. So in a sense, it's more universal. I personally think it will be even harder to prove, and I would encourage young mathematically inclined people here in Trieste to try to do it. Okay, my last slide is an application to this. So we took a model for these oscillations, which is from Peter Ryan some time ago. This is based on these hexamers. I don't have to go into the details here. We used it in a thermodynamically consistent way and calculated the number of coherent oscillations. We calculated the bound, and this is shown here as a function of the driving of this phosphorylation. So the bound is the dashed line. The crosses are the data depending on system size, i.e. how many of these do you have which interact and compete. And you see that taking this semi-realistically or realistic model, the bound is about a factor 2 to 4 off. This is not logarithmic here. So this may indicate that this bound is not too bad. And again, nothing enters this bound. It's a universal bound. Okay, so this brings me to the end. I hope I've convinced you that stochastic thermodynamics can be helpful now in this phase 2.0, where we are basically looking at inequalities, because these equalities, like the fluctuation theorem, do not really tell you much more except yes or no. I'm even more excited about this recent development using thermodynamic inference, and I hope you also like and help to develop these questions concerning oscillations. Let me mention that, of course, students and postdocs have contributed. So the early work on modus was with Eva Zimmermann, Andre Barata, now faculty in Houston, worked with me on this uncertainty relation. Timo Krojuk is a grad student who finished. Patrick Pizonka actually just took over position in Edinburgh. Waiting times are my current grad students, Benjamin Ertl, Jan van der Meen, Julius de Günther, and the oscillations also started with Andre and 2 grad students in my group. Thank you very much.
We have time for a couple of questions. As always, we start with students. Please. Okay.
Come on.
You know, just going back a few slides, but
Which
you know,
one?
don't go back. But you know, I didn't quite understand it. But you had you had a quantity that you were measuring for the steps, for the step size that was
Yes.
getting worse if you got the wrong step size. And I
Yes.
just wonder, I mean, that measuring step size is one of the most notoriously difficult and problematical things for single molecule biophysicists. Is that a method then for being able to actually estimate the step sizes?
It would be great if it was so, yes. So my statement is if you have the x of t trajectory of the beat, using these techniques, you can infer the step size, at least for this simple model where you have just this one step of the motor and not
Because that would be incredibly useful. That would be unbelievably useful because all the step size algorithms are, you know, horrible, basically.
I'm glad to hear this, Joe. I'm glad to hear this.
Okay, thank you. No, it's very nice, the results of the waiting time, and I have many questions, but I will ask about the other technique where you modify the parameters, this slide with lambda.
The time-dependent parameters.
Time-dependent parameters. I guess you are using there the fact that the system is relaxing all the time, and this is reflected by the adiabatic and non-adiabatic entropy production.
We didn't split it into these 2 contributions. Yeah. We didn't do that
And
yet.
you are not using, for deriving this, you are not using adiabatic or non-adiabatic?
No. I mean, the only assumption is that each rate depends on this control parameter in a certain way. It doesn't matter how it depends on it, and that this control parameter is then changed according to a protocol with various speeds. That's all what enters. I think it's very general.
Sorry. Thank you. So you show the result for multiple cycle of
Yes.
length 2.
Yes.
What can you comment what happens if you have cycle of larger length?
Of a greater length.
Yeah, of greater length, because you can have the situation in which you don't have the link backward, so you continue by the arrow for a few more steps until you go back to the initial node.
I'm sorry, I do not understand what you mean. I mean, you can have any number of unobserved links in between. Of course, it may get worse at some point, but as I showed for the unicycle, 1 link is enough. So roughly, the rule is if you have at least as many links as you have independent cycles, you get a full entropy production.
I'm not sure. There's something I think I have not completely understood. So first, you talked about the minimum entropy production without any model, right?
Yes.
And then I'm not sure if I understood. Like you started adding traits of the model. Like for example, you said, okay, I see one transition part, right? So
If I
that's
see-
not model, I'm not sure if I understood
Well,
that.
you see a transition of an underlying Markov network. This is
Yes.
this. Or you see several transitions.
Yes.
Now you could also say, yeah, but what happens if I lump transitions? If I cannot distinguish this transition from this transition? And this is something...
Is that equivalent to adding like aspects of the model, like saying, okay, I do not know anything. Okay, I know at least that something
I wouldn't say
transitions
you're
are-
adding to the model. I think I would say you add to your measurements. You add to your data.
Okay.
And you
so
see in this most recent work here, we're even more general. I mean, we just have events, and we have times between events. And what we need is, that's why it's called Markovian snippet. You need one state which is Markovian. That's enough.
Okay, so what you are trying to search, what's the minimum entropy production for the measurements you have. We are asking out the model.
Yeah, we have, what is the minimal entropy production in this whole system? I do not see, based on what I see, without assuming topology. Like, for instance, Julie Bisker yesterday, she was assuming, okay, I have 4 states and I only see 3 or so. I mean, this is in a sense model-free.
Okay, so at some point you showed this curve of ratio between waiting times from which you extract maximum and minimum.
Yes.
And you were saying that, so I imagine that the more complex the geometry of your network, the more complex these curves.
Yeah.
Does it also say something about different timescales that exist in the hidden networks?
It certainly is related to this, but I would not be able to make a definite statement about this. A quantitative statement. But clearly, I mean, the time scale of variation here of this curve reflects intrinsic time scales of the network. You're perfectly right. But this is something we haven't tried to figure out in detail yet.
Thank you.
Yes, here. So, so could you summarize or perhaps comment on the importance of the existence of these mesoscopic states, right? So proteins often have a plethora of small local minima of half kT or kT deep, and yeah. So what do they do to this?
It's a crucial input that on some underlying level you have a Markovian dynamics. And if that is not fulfilled, none of this can be done. But I guess if that is not fulfilled, many other things beyond MD cannot be done either.
That's what you will have to start with. Indeed.
You have to start, that's why I had it on my second slide or so, you have to start with this idea that there are identifiable mesostates. You do not have to see them all. Now, in these new developments. You would have to see them all if you wanted to apply fluctuation theorem, but these inequalities can be, but yes, I mean, it's a very good point, and it would be interesting to see if there is a way to relax this assumption. It's a very good point, Peter Ryan.
Thanks.
All right, we can thank the speaker once again.